So I'm going to talk about recent results from BELLE 2, which is the beauty, and LHCb, which is the beast. The beast in a positive sense, in the sense of a lot of nice and new results. So we all know about the great success of the standard model, and I'm not going to repeat this here. And basically, this part of the iceberg is the reason why most of us are doing this today. And these two experiments, BELLE 2 and LHCb, are trying to understand something about that submerged part of the iceberg. And this could be understood through the indirect way, so trying to find the signs of virtual contribution, or contribution from virtual particles in low energy processes, which, as this plot shows, assuming some, of course, some assumption, will reach new physics scales that can exceed a lot what you can achieve directly through LHC or FCC. These are mixing observable, CP violating, or CP conserving, and you see that you can get various order of magnitude above the direct reach. So this is the indirect way to finding signs of new physics, or we can also try to look at the direct discoveries, which in our case are restricted mostly to light dark matter searches through these dark sector scenarios that are explained in these slides here. But basically, the thing is that we know that dark matter is likely to exist, and the dark sectors have been proposed in the past 10 or 15 years as a good solution to many, both for dark matters and to many other puzzles. And so there are only a few options of coupling that do not violate standard model symmetries, which make the systematic exploration possible. But on the other hand, there are not enough results for setting very strong constraints. So we are in a very nice position to investigate those, and I will briefly touch on those two. So these are the two players. In essence, LHCb produces many, many more signal events and much more displaced from the primary vertex, which is an advantage. But it's hard to reconstruct final states that contain neutrinos or pi zeros or photons. BELLE 2 produce much less signal in a much clearer environment and with a more hermetic detectors, which makes the reconstruction of final states with photons, pi zeros, neutrinos easier, quote unquote. So in what follows, I will just hype up the anomalies. Now, it's not true. I will just try to tell you what I just said at the beginning. I'm trying to make the case for a unique opportunity in the field of flavor physics, but also beyond that, of having two experiments running simultaneously in complementary environments. And here, complementarity really is the name of the game. So since apparently no talk is sexy enough without many mentions of the anomalies, I will try also myself here, and I will start from material that is supposed to not show any anomaly, okay? The stuff that are rooted in the 3-level standard model. And of course, the first is the measurement of the angle gamma, or the VUB phase, roughly speaking, which is this guy here, which determines the size of CP violation in the standard model, essentially. And this is a very nice quantity, because if you measure it to 3 decays where you do not expect large new physics, it's actually a very robust gauge of the standard model with a very precise prediction of 1 part per million or so. And you exceed this through the interference of these decays of B minus to D0 K minus or anti-D0 K minus. And you can see that this guy is sensitive to VCB, this one other to VUB. And then, of course, you have some hadronic parameters associated with the decay amplitudes. But in the end, the experiments and the theorists have developed a very, very sophisticated and careful way of extracting gamma or phi 3 in a very precise way through B to DK decays. And basically, the most sensitive method is based on some looking at asymmetries distributed in opportunely chosen bins over the Dalitz plot. And yeah. You mean new physics in the trees? Yeah. So, but you would have many signs in many other decays, right? You would have, you know, deviation in many other decays. Because B2 charm is favored, so you would have many other signs of this happening in many other channels, right? At least if I got your question right. All right. So this is really the terrain of LHCb that combines many different measurements. I'm not going to go through details. This is the most sensitive one. So you see, these are the asymmetry that you observe as a function of some beams in the Dalitz plot. And you see that if there was no CP violation, you would expect all the things scattering around here. And you can clearly see that there is large CP violation, very precisely measured. A more perhaps intuitive way of seeing it is another channel with decay of the charm in 4 atoms, where you can see that in some beams, you have even 90% almost CP violation. You see the difference between these two purple peaks is huge, okay? So LHCb does this measurement and combine them together to find a determination of the gamma with an error that is less than 4 degrees, okay? Less than 4 degrees. BELLE2 here cannot compete on the precision, even though BELLE2 has the first result with a combined BELLE and BELLE2 analysis, in fact. And it's nice that it was actually driven by an Indian student. And of course, you can see from the uncertainty that we are not competitive with LHCb at this time. But down the line, when the global uncertainty will be of the order of 1 degree or less, we expect the systematics will be important. And at that point, it will be very important to have 2 different experiments with different systematics checking each other. Then another thing that is dominated by 3 decays are the measurement of the strength of the B-quark coupling to C and U. These are the guys that determine this apex here through this constraint. And here, in fact, there is the first anomaly, if we want to call it such, is the fact that the determination of these parameters happens through semi-leptonic decays, okay? And you can choose to reconstruct only one channel, one semi-leptonic channel, then combine with QCD lattice inputs and get one determination. Or you can have a different determination where you actually look inclusively at many final states, and you use operator product expansion in QCD, and you get another determination. But you expect these 2 guys to converge to the same value. And you can see from these bands here that there is both in VUB and both in VCB and in VCB a difference, a systematic difference between the inclusive and the exclusive determination. So this, many call it an anomaly. Some people even try to interpret it in terms of new physics. But I think that most people think this is likely to be either a theoretical or an experimental blunder, most likely associated to the inclusive part, which is the most difficult. And so here, what we're trying to do is to diversify the portfolio. You know, when the market is uncertain, you diversify. And so there are many measurements across many mesons, channels, approaches, and here is a short list. And the nice thing is that while this has been traditionally the realm of B-factor experiments, LHCb has been weighting very, very strongly with a very nice measurement directly of the ratio, which is the important quantity, between VUB and VCB, through this ratio of branching fraction of BS decays. So you have BS to K mu nu, which gives you the VUB thing, and BS to DS mu nu, which gives you the VCB. And then, of course, these are very difficult analysis because you have neutrinos in the final state and you don't have a discrimination of the signal that is very precise. You have to, you know, see the signal is this green thing. You have to try to fit your signal, which is buried in this large background. So the sample composition is very critical, and you have to do many cross-check, many control channels to make sure you understand what you're doing. And in the end, the results are very, very precise. And I think this is a very nice demonstration of an ingenious use you can do of the peculiarities of hadron collider physics. So you have B sub S decays, which you do not have in, at least you do not have in large abundance B factories, and you have large boost, which gives you the possibility to construct the BS direction and build these variables here. BELLE 2 is too early to provide actually very competitive results, but the factory is at full steam with many different results on VUB and VCB in various different ways. So if you look at the future, we're looking at something that, depending also on lattice QCD advances, will go to precision of the order of 2% or so. But of course, we will only get there if we figure out the discrepancy between inclusive and exclusive, which is probably the most pressing issue here. Because without that, we'll just make the discrepancy larger with more precise measurements. Now let's go to the real anomalies. Let's start from the tau excess that has been observed by various experiments since already 5 or 7 years in B to C transitions. Again, here this is 3 transition. This is also called RD and RD star. And basically you measure this by measuring this ratio of branching fraction between D star to tau nu and D to tau nu versus the lighter leptons, E and mu on the denominator. And what you see here is that the standard model prediction is somewhat far from the average of the other experiment. 3 sigma, 3.2 sigma, 2.9 is not important. There is a pattern that is consistent of being far from the standard model prediction. So if you want to interpret this in terms of ineffective field theory, you can imagine that there is some, for natural coupling, some standard model, non-standard model physics of the order of a few GeV mass. Where do we stand here? This is a long-standing discrepancy. So we have been continuing to investigating. One of the last contribution has been the simultaneous measurement, the first simultaneous measurement of both RD star and RD by LHCb in hadron collisions. I think this is one of the most difficult measurements one can try to do in hadron collisions because the numerator has 3 neutrinos. So it's really very, very difficult to find a distribution where you can distinguish the signal. You see, this is the data you see, and this is what you're trying to separate using simultaneous fits of signal-enriched samples, control channels, etc., etc., etc. This looks very, very difficult, and it is. These are very long analyses, but in the end, the results are very nice. They are not as precise as the best results from the B factories, but we are getting there. They are getting there. So this is just an example of what you can really do when you have so much signal as LHCb has. So where is the perspective here? I think that, despite the LHCb efforts, I think here the drive will be on BELLE 2, because BELLE 2, these analyses are significantly easier in B factories. And BELLE 2 can also access other quantities, not only RD and RD star, which is the exclusive quantity, but we can also measure Rx. So you will just not reconstruct the charm meson and you just look at it inclusively, or you can even do these ratios using pions. So this is a plot that shows as a function of the data sample size where the precisions of these various ways of accessing the same anomaly can get us. And what I think will happen next year is that we might have new results, not only from BELLE 2, but also from BELLE, and maybe also from CMS, Atlas, etc., etc. So I think this is one of the things in which we want to focus our attention soon. Part of this process of looking at the inclusive ratio, something that is basically has been done only in the early 2000s at lab and never done after, is to look at the ratio of the electron over muon, which is one of the latest results from BELLE 2, where you basically try to find lepton flavor universality between the two light leptons. And you do it in a high part of the lepton spectrum when you do not have no more any taus. And the results are actually very, very intriguing. We have, of course, we have a result that is compatible with Lepton-Flavor universality, it's 1, but the uncertainties are very, very competitive. And this was something that BELLE did not expect, was just an intermediate step in the analysis of the Rx, of the inclusive one. Further real anomalies are those seen basically by LHCb only in muon deficit on B2S transition, which are also called RK, RK star, RK short, etc., etc. So basically also here you're just looking at the ratio of two rates of B2 strange mu mu over B2 strange EE. These things have a very solid prediction, because QCD uncertainties are very small and radiative correction are also small. And you can see here in this collection of results that the measured values are all lower than what you would expect from Lepton-Flavor universality. So from the property that leptons only differ by themselves only by mass, nothing else. And this coherent deficit is what excited many people in our field, also because it was accompanied by other tensions that were consistent with that. This is a tension in the branching fraction as a function of the muons mass square. However, here the predictions are more uncertain. This is a tension on a special angular variable that suppresses the hadronic unknowns, etc., etc. So this coherent picture of anomalies have, of course, triggered a lot of excitation in the field. Many people are trying to, fit a non-standard model, Wilson coefficient that were compatible with all of these anomalies. There have been some model building. And one of the most popular explanations for this is a revival of the lepton quarks, which are colored triplet bosons carrying lepton and baryon numbers, which suggest a next unification between lepton and quarks. And you can see the interesting part here is that some of these models predict or suggest significant enhancements or changes with respect to the standard model prediction in many other families of channels. So K star, K tau tau, K star nu nu, K tau mu, etc. So it's obvious that from an experimentalist point of view, the next thing to go is to go and look at those guys. But before getting too excited, let's also examine the possibility of experimental non-universality, right? Because while the theory here is clean, the experiment is much less cleaner, especially in hadron collision. You have differences in efficiencies in reconstructing muons and electrons, and those are nicely suppressed by doing double ratios with respect to the J psi, to the resonant channels, okay? So that part, I think, is very solid. But there are also differences in background. If you compare the background you get into the electron here, with respect to the background you get to muons, you see that there is a lot of difference. And this difference is not obviously taken care of by using the normalization with the J psi channel. In fact, here, this background is in size and in composition quite different from this one. So this is clearly one of the delicate points of those analyses, especially in hadron collisions. Because at the B factories, you see that the situation is also visually seems easier, seems more symmetric, right? These are the electrons, these are the muons, this is a latest BELLE result. This is the preliminary BELLE-2 result, but look at here, and you can see that the picture of backgrounds and in both the resonant and the non-resonant channel are much more comparable in a way. So I think that, however, here you pay that you have less signal, of course. So I think that a nice way of putting that is that LHCb will unquestionably drive the determination of the size of the effect, if there will be an effect. But of course, and BELLE-2 will not compete in the precision, but of course, these considerations about the real differences between electron and muons, for instance, in the background, we'll need BELLE-2 also, because BELLE-2, with more statistics than now, with 5 to 10 inverse autobahn, may prove the check, at least, the presence of the effect, even if not contributing much to the precision. So again, this is a clear case of complementarity. Yeah. And of course, another thing is to look at the other channels that are enhanced in the models put forward to explain those anomalies. For instance, BELLE-2 and BELLE are doing a significant campaign to explore, auxiliary channels that expect enhancement if these things like Lepton quark of non-standard model Wilson coefficient are there. So we have measurement of B plus to K plus nu at BELLE, which achieves a much better precision with only 1/6 of the current BELLE sample. You see, we have a precision that is already comparable with the best measurement from the previous B factors, the full sample. And also we have a recent result of B0 to K star tau tau at BELLE, which it's a very difficult analysis, very, very difficult. You see, they look at the signal as an enhancement at 0 of the calorimeter energy not associated to a B bar. And they put the first direct limit at 2 × 10⁻�3. So there is a whole campaign going on here. And of course, it touches also another very important channel that has been pursued at LHC, especially LHCb, but also CMS, which is BS to mu and B to mu, with very nice new results, very strongly constraining combination. And it's actually very surprising that currently the most precise result, even by very little, is by CMS. This is really a nice a nice proof of the power of hadron collision also in doing precise flavor physics. There are, I'm finishing, some things that are not anomalies today, but may become anomalies one day. This is just a joke, just to hype up the anomaly thing. LHCb is doing a lot in charm physics, order of magnitude advances in our understanding of charm CP violation, with the first evidence of CP violation in a single mode here in a direct CP violation in pi, represented in these plots here, and also the first evidence of a mass difference between the charm eigenstate and the first very tight constraint of CP violation in the mixing. And of course here, these things will further improve with more and more statistics. But I think that in order to see whether this stuff is compatible or not with the standard model, we need to wait theory, because at least my understanding is that theory is currently a bit behind on this for the obvious difficulties associated with the charm mass values, etc. And of course, in the meantime, BELLE-2 will explore, and LHCb will explore also beyond the standard model physics in penguins through time-dependent CP violation penguin loops, K short, K short, K short, eta prime K short, phi K short, etc., etc. And the same thing will happen with the B sub S, phi phi, K star at LHCb. So here, this is another very clear-cut example of complementarity where you explore the B0 sector at BELLE-2, you explore the B sub S sector on the same physics at LHCb. And finally, the far-out anomalies, we all know that the G-2 confirmation of the BNL result made news last year. And we're trying, for what we can, to also contribute here. BELLE-2 has a recent result on an invisible Z prime search in a final state with mu and missing energy, which is basically a bump hunt in this spectrum of the recoil mass to the square. And this model is not one of the 1,000 models you can test, but it's particularly interesting because it's one of the most economic models that could explain the G-2 anomaly. So you see, this is the G-2 anomaly, what you would expect if it was caused by a Z prime with this characteristic. And this is the exclusion limits by BELLE-2, which, as you see, exclude this explanation in the range from 1 to about 5 GeV for the hypothetical Z prime mass. And we also try to contribute to the standard model side of this. You know that the G-2 standard model prediction based on dispersion relations are I'm done, 1 minute, are basically crippled by the fact that the hadron vacuum polarization input that comes from experiments is inconsistent between Chloe results and Babar results. So here, BELLE has clearly an opportunity to contribute. If we can manage to find a measurement that is very precise and very convincing, we can settle this and help improving the precision of this theoretical prediction. So we're just, making the first steps in this direction with a measurement of E plus, E minus 2, pi plus, pi minus, pi 0, which is not the largest contributor to this uncertainty, but is significantly easier than the pi, which will follow. And so we thought it was a good way of starting from there. Okay, sorry. So this is my summary. I don't think I need to repeat it. I already said it many times, and that's the end of my talk. I hope it's not the end of these topics, though. Thank you.
Tonnelli, for this nice coverage of a huge topic. I see quite a few hands raised. So let us start with the younger ones. So, okay, you. Not so young.
Hi. So from the reports of BELLE, I see that there is some plan to measure asymmetries in tau decays, like tau plus 2, tau plus 2 pi plus k0 nu and tau minus 2 pi minus k0 nu, so on and so forth. And in many cases, I see that you have this tau to k0 and stuff channel that you expect to measure very precisely. But I never see the tau to k plus pi 0 channel mentioned as frequently. Like, is there any reason for that, or just because of the observables that you are more interested in? Or is there some deeper experimental thing going on?
No deeper experimental thing going on.
So is it?
We just prioritize our topic depending on the data we have and the people we have. But
so if one, like, let's say hypothetically can give you a scenario where you can, like, it might be useful to probe the tau plus, like tau to k plus pi 0 nu channel, and then take the ratio with the tau plus to k0 pi plus channel. Like, if it can be theoretically motivated, then there's no reason why you cannot look at that ratio at a very high precision. Okay, thank you.
Okay.
Yeah, thank you.
Yeah, so I'm here. So I have a question on slide 23, where you showed that formula for lepton flavor universality and how you probe that. Yeah, this one. Yeah.
Oh, this.
No, the lepton flavor universality. I guess it was the slide we just flashed by.
This?
Yeah. So in this formula, when R strange going to basically the ratio between the branching fractions of mu plus and E plus E minus. So what prevents you from computing this in the tau sector as well? Say tau to mu or E to tau. What's wrong with that tau reconstruction, say in the hadronic channel?
Yeah. There are tests of lepton flavor universality. So you mean tau decays?
Exactly, tau decays.
There are. We're pursuing them, and people have predictions for that.
Like combining the results for the two channels. That was my question. Like, are you working on that as well?
Yeah. We're working on everything. The difficulty is getting the result out.
Although this is not the main topic of your talk about the G-2, as you said, there is an inflation in the error because of the inconsistency between Chloe and Babar, and that you could settle that. And yet, even with that inflated error, there's no way one can account for the discrepancy between the experiment and the theory today. And this, of course, look at the lattice, which is somewhere in between. And yet, I think the lattice error is probably underestimated. But it would definitely be very interesting to see how you would settle the Chloe versus Babar. But even if you did settle that, that will not settle the discrepancy between the theory and the experiment. Just thought that.
You don't know. Maybe they were both wrong. We are the other way around.
That would just be
No, I know,
Highly
I know.
implausible.
I don't, you know, I'm not an expert in that. I know that, you know, perhaps if we do things carefully, we can settle the thing, and this will perhaps even stretch the anomaly with respect to the dispersion related basis. But I also seen, as you said, many recent work on the lattice that seems to point to a smaller uncertainty with respect, a smaller discrepancy with respect to the experimental results. So I don't know, maybe someone more expert than me should comment there. The update by whom? By LHCb? My understanding, so I'm no longer in LHCb since a while. My understanding is that they are working on a joint analysis of RK and RK star in the same flow, much similar to what they shown RD and RD star. And of course, since the sensitivity now will be very, very high, and they are doing their work very, very carefully in order to make, to give a message that will not leave any open questions. There is an illustrious member there, maybe.
Is there any other question? I hope we can go for the next speaker. So thank you for this nice talk, Tonnelli.